Hello, I'm Blake Fahrenholtz, and in this video I'm going to teach you a bit about astrobiology. Time is limited, so let's jump right in. We'll begin by discussing the philosophical foundations of astrobiology in ancient Greece. We'll then cover some thought change during the Renaissance and go through to the 1800s. In ancient Greece, some foundational pieces of astrobiology were seated. Metrodorus is quoted as saying, "It's not natural in a large field to get only one ear of wheat, and in an endless universe only one living world. That it is infinite in plurality is evident in that the causes are infinite." Democritus, who first formulated the atomic theory and gave us the word atom from his atomos, expanded, saying, "The innumerable worlds are full of life, as a random result of the aggregation of atoms, some worlds like our own and some very different." And finally, Epicurus is quoted saying, "There are infinite worlds similar to and different from our own world. We must believe that in all worlds there are living creatures and planets and other things we see in our world." During the Renaissance, evidence started to unravel the universe. We adopted the heliocentric model and explored space in greater detail with the first telescopes. However, before these happened, Giordano Bruno shared his vision of the universe. For his ideas, he was quickly vilified by the church. He realized that innumerable celestial bodies, stars, globes, suns, and earths may be sensibly perceived therein by us, and an infinite number of them may be inferred by our own reason. In 1698, Christian Huygens, who discovered Saturn's moon Titan, published the book Cosmotheros, in which he declared God would not have let other worlds be barren. Arguing the opposing side of the intent of the divine, William Whewell argued that other worlds would be uninhabitable. Mankind and the earth are uniquely important to God, in his book On the Plurality of Worlds. With these philosophical foundations set, we'll now jump into the true beginnings of astrobiology. The field began in 1953 when Russian astronomer Gavril Tikhov coined the phrase astrobiology. Its sister term exobiology was introduced by American molecular biologist Joshua Lederberg. NASA funded Project Viking, its first investigation of life in space, in 1959, and founded the exobiology program in 1960. Other projects at the time included Sputnik, the first probe in space that was launched in 1957, and Project Cyclops in 1971, shortly after the Viking rovers landed on Mars in 1970. Project Cyclops was part of SETI, the Search for Extraterrestrial Life project. The focus of this project was to search for, decipher, and compose messages that could theoretically be understood by another technological civilization. They set up ground-based satellite arrays to detect and create radio broadcasts. An example of this is the Arecibo radio telescope in Puerto Rico. Its dish is 1,000 feet in diameter and 167 feet deep. In 1974, it sent the Arecibo message, which is a 3-minute long encoded message that can be decoded to create a 73 by 23 pixel image, which is shown on the right. It displays a man, DNA, the Arecibo telescope, our solar system going from Sun to Pluto, and depictions of different biological molecules. This message was sent as a total of a 20 trillion watt omnidirectional broadcast aimed towards a globular cluster 21,000 light years away. This message is bright enough to be seen by a similar sized telescope anywhere in our galaxy. Notable scientists, including Stephen Hawking, warned that such messages may lure alien civilizations to steal our resources, while others like Carl Sagan advocated for communication attempts. The Viking rovers 1 and 2 landed on Mars in July and September 1976, respectively. They carried out experiments described by Harold Klein et al. In the journal Science in October 1976. The pyrolytic experiment had the rover take soil samples into a container and add radioactive carbon-14 tagged carbon dioxide gas. A small amount was detected to be turned into organic material. A duplicate trial was then first heated and then exposed to carbon dioxide, and this trial seemed to prevent the change. It seemed to have no change. The gas exchange experiment had rovers humidify soil samples for 6 sols, or Martian days, before wetting with a complex aqueous solution of metabolites. The gas above the sample was monitored by gas chromatography. Initially, there was a substantial amount of O2 gas present, but subsequent detections yielded significant increases in carbon dioxide. Finally, the labeled release experiment had the rovers moisten soil with several carbon-14 labeled organic compounds. Substantial radioactive gas was registered, but a duplicate heat-treated trial again yielded no results. These experiments were eventually judged inconclusive because inorganic means could yield similar results. Now let's take a look at some more modern Mars missions. In 2003, the European Space Agency landed Beagle 2, named after Darwin's ship, on the surface of Mars. Its mission was to look for signs of life. Unfortunately, after landing, it could not fully deploy its solar panels or its telecommunication antenna, and the project quickly ended. Curiosity and Perseverance have been incredibly successful, though, and we'll focus on them next. Curiosity landed in Mars's Gale crater in August of 2011. This site was identified because satellite imagery by the Mars Reconnaissance Orbiter and Mars Express indicated the presence of clay and sulfate minerals. This indicates that the crater once contained a lake. An article by James Green, a former chief scientist at NASA, states that Curiosity drilled under the surface of Mars because 1 to 1.5 centimeters under the surface, the soil is dramatically different. The samples analyzed by Curiosity showed the presence of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. The soil was moist and also contained nitrates. This further evidences the prior presence of a lake at this location. The liquid water being present also demonstrates that an atmosphere containing sufficient greenhouse gases was likely present, enough there to keep water warm. Curiosity also detected complex molecules such as benzene and propane, as well as kerogens, which are larger macromolecules that are associated with algae and woody plants here on Earth. Perseverance landed on February 18, 2021, on Mars's Jezero crater. This location was chosen because there's evidence that this area was a large ocean 4 billion years ago that had a river flowing to it. After the meteor struck this location, the river filled the crater with water and slowly built up sediment in the delta over time. This slow accumulation of sediment is hoped to be similar to Earth's river deltas at the time. They were able to, to preserve fossils such as stromatolites. This image, captured by Perseverance, also shows its companion drone, Ingenuity. This image I've added in to show a picture of the landing site in Jezero crater. You can see off to the side that the maps indicate that there would have been a river here in the past, and you can see the river delta that Perseverance is investigating here. We'll next briefly highlight 2 upcoming Mars missions that are going beyond Mars. The Europa Clipper is an orbiter that launched in 2024 and is bound for Jupiter's moon Europa. It's scheduled to arrive in 2030. Dragonfly is a future project set to launch in 2028. Its different design is an octocopter drone the size of a car that will fly 50 miles between different points of interest on Titan over the course of its mission. Maybe we'll discover that Christian Huyn's discovered moon was, in fact, not left barren as he predicted. Next, we'll investigate modern space based astrobiology research. Shuttle Life was an experiment carried on the Shuttle Endeavour in May of 2011. The experiment exposed 6 dormant types of microorganisms, including bacteria, archaea, and 2 types of tardigrades, to low atmosphere conditions in small puck-shaped containers called Derlin tubes. Basically, it was a synthetic rock that they're being encased inside. The experiment showed successful survival for extremophile bacteria, archaea, and tardigrades. This was a trial run for a larger, later Phobos Life mission, which was to be carried um, by carried to Mars's moon Phobos and back by the Russian Phobos Grunt spacecraft. Unfortunately, the secondary propulsion system failed on this mission and the experiment was destroyed. Expose R2 was a mission on board the International Space Station. 600 biological samples, including fungi, plant seeds, triops eggs, mosses, and cyanobacteria, were exposed to conditions similar to those on the Martian surface. Exposure lasted 531 days, with some having unprotected exposure to solar radiation for the final 469 days. Results of interest include cyanobacteria that were reported by Bach et al. After having long exposure in solar radiation, cyanobacteria carotenoid pigments, which are used to protect DNA, were still detectable. Finally, we're going to take a look at a few examples of interstellar biochemistry. In January 2024, Rocha et al. Published in Astronomy and Astrophysics the absorption spectra of 2 protostars. The detected signatures indicate many organic molecules, including methane, sulfur dioxide, the forma ion, and cyanide ion. They note that these 2 together indicate that acid-base reactions may be common in interstellar ice. Also ethanol, acetaldehyde, methylformate, and they said likely acetic acid, only likely because it was only found around one of the 2 protostars. Finally, I wanted to share a very recent development from July 13th, 2026. This was published in Nature Astronomy. Erythrulose, which is a 4-carbon sugar, was found in interstellar medium using the Yeebs 40M and IREM 40M ground-based telescopes. Previously, ribose and glucose have been found on asteroids, but this is the first sugar that has been found in the interstellar medium. Thank you for watching.